So, there are two methods for the determination of absorbance in turbidimetric methods, and as you can see, we can make the measurement in the same wavelength, in the same direction of the electromagnetic radiation after this radiation passes through the sample. Then it is known as turbidimetry, and when I make the measurement perpendicular to the electromagnetic radiation, then it is known as nephelometry. I can show you a simple example. So, this is my incoming radiation corresponding to a particular frequency, that is h mu, and then after all this slate etc., and then other things, I have the sample compartment here. And then I have the detector. So, this is the basic schematic diagram of a spectrophotometer. So, if I am measuring the radiation in the same direction, that is along this direction, then it is known as turbidimetry. In turbidimetry, generally what happens is the opposite sides of the cell are polished. This is cell. Opposite sides are polished in turbidimetry. But in nephelometry, the one side of the opposite side is not polished, only one side is polished. So, if I have a cell like this, incoming radiation, this is polished and this side is not polished. This side is polished. So, in nephelometry, opposite side is kept rough, but the bottom side of the cell is polished. So, the radiation will enter like this, go through the cell, and then the detector is placed at right angles to the incident radiation. This is the major difference between the two cells, between turbidimetry and nephelometry. Okay. So, but otherwise there is not much difference, except that the measurements, the optics design for nephelometry is slightly different from the turbidimetry. Only in this aspect it differs. So, usually nephelometric instruments are preferred for samples having transmittance greater than 90%. That means for very low concentrations in water and wastewater samples. So, at 90% the concentration is least sensitive to variation in particle size, because the concentration is so low that the getting a linearity curve is not a big problem at all. And then sometimes simple optical systems can be used for the determination that is relatively free of stray radiation. For this reason, nephelometers are basically filter photometers, but with a slight design change, and turbidimeters can be ordinary spectrophotometers. So, in many times in spectrophotometry there is no model or there is no accessory for turbidimetry, but there will be an accessory for nephelometry. On the other hand, the for nephelometry there may be a dedicated instrument available whenever you need one. So, normally spectrophotometric cells are also made to be useful for nephelometry. So, when a narrow beam of radiation strikes the surface of the sample at a very small angle, part of the reflected beam strikes the water surface and escapes into a light trap. The remaining portion enters the sample at 45 degrees, and if any particle turbidity is there, then radiation scattering occurs and some of the scattered radiation reaches the detector. So, the positioning of the detector is also very important in turbidimetry. Such an instrument as can detect turbidities up to 0.01 NTU. NTU is a unit turbidence units, nephelometric and turbidimetric unit known as 0.01. There are standards for water analysis where the turbidity is defined in terms of turbidence units NTUs, and platinum chloride is one of the standards used for calibrating the turbidence units. So, in turbidimetry small amounts of insoluble compounds are prepared in a state of aggregation. Now, we come to the chemistry of the method. So, what do we do whenever we want to make the measurements in turbidimetry? All you have to do is continue doing a chemical reaction as if using your standard flask, chemical reagents, etc., for which we will come to that again in at a later stage. And we are prepared, what you have to do is to prepare the reagent and standards, mix them in suitable proportions under optimum pH conditions, etc., temperature conditions, pH conditions, shaking conditions, etc. And once you make the standards ready, then you have to pass the light through such a suspension, and the fraction of energy dissipated by absorption, reflection, scattering, etc., it is measured with respect to the incident radiation and displayed as the ratio of the P by P naught or absorbance or transmittance. Now, for such suspensions, Beer-Lambert's law is obeyed up to a particular concentration, and analysis can be performed just like spectrophotometry. Since the results for turbidity are at best empirical, as I have explained to you a number of times, whatever way you prepare the standards, next day if you come and prepare, unless the conditions are extremely critical and exactly same, you will not get the same absorbance. Therefore, the results for turbidity are at best empirical only. So, that means the error margin with respect to the concentration is fairly large with respect to as compared to spectrophotometry, and there is no sound theoretical basis to determine the absorbance theoretically. There is nothing like molar absorptivity or epsilon value like that in spectrophotometry with respect to turbidimetry precipitation methods. So, the construction of calibration curves is always recommended. Every time you want to do a turbidimetric determination, we recommend that you prepare your calibration curve on the same day, same time. Whenever you want to make your measurement, unknown measurement, at the same time the standard should be prepared and standard should be mixed along with the sample under similar conditions, and that data will hold good only for that set of samples and calibrated standards as far as turbidimetry is concerned. Next day again you come and do the calibration, do the measurement, and continue working with the same solutions. Even if you the reagents are all same, the absorbance will be different. So, we say we recommend strongly that every time you every time you make a measurement, check the calibration first and adjust it accordingly for small experimental variations, because 99% of the time it is only empirical correlation. So, the experimental conditions should also be exactly reproducible as far as possible. So, what are these absorbance conditions? So, in turbidimetry we need to follow the conditions, something like concentration of substances participating in the reaction. The standards must be prepared scrupulously, and then substances, other reagents also must be prepared very accurately. So, there is no need to overemphasize that all the standards and reagents must be particle free. It should be of very high clarity standards. There should not be any suspended particles, undissolved substances, etc., in the reagents. That is number 1. Number 2 is order of mixing and the rate of mixing. Sometimes we take metals, then add buffer, then add reagent, and if you do then a stabilizing agent to keep the small particles in suspension. Now, the order of mixing can change. I can change it, take the reagent first, add a stabilizing reagent, and then add your metal, add the buffer, etc. You can prepare the precipitate in a 4 factorial ways, but it is important in all turbidimetric methods that order of mixing should be exactly same for the standard and for the sample. So, otherwise there will be variations in the recordings, in the absorbance measurements. Then we need to use protective colloids such as gelatin, gum arabic, dextrin, polyvinyl alcohol, etc. These are all basically viscous solutions which will make the particles move slower. So, what happens if I take the substance, in a bottle and then I add a protective colloid to that, the system becomes viscous. So, the viscous solutions, if I mix them by gentle shaking, something like this, slowly, something like this, shake 1, 2, 1, 2. This way we can shake, or I can shake it like this, or I can shake it like this, put it in a machine to shake it like this. There are different ways of shaking, and once you put the viscous solution, the shaking should be very uniform and very gentle. That is very important. So, all these things approximately in about 1% I have to use gelatin, gum arabic, dextrine, these are all basically gums and high molecular weight substances. So, that is important for us, and then we also should be worried about the presence of other salts. That is a basic concept of spectrophotometry, that is matrix matching. What are the substances in your standards? It should be there in the sample also, or whatever, or the other way around, whatever is the sample matrix, we should try to match it in the standards. So, presence of other salts is important, and also we need to determine the temperature at which we carry out the reaction, because we know that solubility of a precipitate is a temperature dependent function. As the temperature increases, solubility will increase, and if the solubility increases, absorbance is going to be affected. So, you will get lower absorbance, but if the temperature decreases, solubility will decrease, and there will be more particles, more scattering, more transmittance, and you may get higher reading. So, in all these cases, these 5 parameters one has to look carefully with respect to making a standard measurement. In theory, I can make any precipitation reaction amenable for spectrophotometry, provided they can be prepared in a reproducible manner, and we know that there are several millions of chemical reactions including pharmaceuticals etc., which are precipitation reactions. So, excellent results in sub parts per billion level have been obtained. For some of them I am listing below here, that is determination of barium sulfate using glycerol alcohol as a stabilizer. Now, you will be surprised that how many times we do the determination of sulfate in water. Actually, the presence of sulfate in drinking water is a subject of regulation and standards, effluent standards. So, there is if the water is very hard, drinking water is very hard, we suspect that calcium and magnesium sulfates are the cause, and in drinking water it should not exceed more than 200 ppm. So, the sulfate 200 ppm means you cannot do the determination by titration and other things, even though EDTA can help in such matters, but this is an excellent example of how the simple analyte, that is sulfate ion, can be determined using spectrophotometry. Now, all you have to do is take sample containing barium sulfate, add a little buffer to adjust the pH, add barium chloride solution. So, you have barium sulfate will precipitate. To keep the precipitate in solution, what you should be doing? You should add using glycerol alcohol, you can add polyvinyl alcohol also, and then several other gums, dextrines etc. can be added, and this is one example where the gravimetric or spectrophotometric finish to a gravimetric method can be easily adopted. The advantages in such cases is you can finish the spectrophotometric analysis in about 1/10 of the time that is required for gravimetric determination as barium sulfate, and also it is possible to reduce the time and accuracy will be much better. In our laboratory we have developed these methods and standardized, and we have prepared a cookbook which will tell you what should be the absorbance, approximate absorbance within the working error, what you should be looking for. So, going back to this, The another example is determination of phosphate as strychnine phosphomolybdate. This is also a very important concept for the determination of phosphate. Strychnine phosphomolybdate precipitates as a yellow powder, and then if it is in water it can be held in suspension using polyvinyl alcohol, approximately 1 ml of 1% in 25 ml. That is the idea, that is the range in which we will be working. So, most of the stabilizers are 1% solutions. We need about 0.5 ml or 1 ml in a sample of about 10 ml, 25 ml, 50 ml like that to keep the precipitates in suspension. So, ammonia is another example, which is a very well known pollutant and a chemical used in day to day life also, and an excellent method exists as Nessler's reagent, and Nessler's reagent produces a precipitate of potassium mercurate, potassium ammonium mercurate, and that can be determined using Nessler's reagent. This is also a very good method for the adoption of turbidimetry in spectrophotometry. So, these are some of the examples which will give you sub ppb levels. So, that is less than microgram per ml. And as far as instrumentation is concerned, I have already explained to you that turbidimeters and nephelometers resemble filter photometers in instrumentation. They are also available as accessories to our ultraviolet and visible spectrophotometer. Such instruments provide a practical way to continuously monitor the turbidity also, just like FIA in water, flow injection analysis, and determination of the clarity of beverages, Coca-Cola, Fanta and all these drinks, beverages can be their quality can be controlled using turbidimetry. And there are several pharmaceutical preparations, product quality control, boiler feed waters, condensates, and for all these things phosphate is required, sulfate is required analysis, and turbidimetry could be one of the best methods for easy and fast determination of such samples. It's okay. Now, I will not say more about the turbidimetry and nephelometry, but we will move on to another aspect, spectra of solids. Now, I want you to concentrate on what I am going to show you, what I am going to tell you. Sometimes it is possible for us to monitor the color of the solid particles. Quite often you would see a nicely painted car on the road. You will be tempted to look at it, oh how nice the car is, and etc., etc. But you will be wiser to know that several parts of the car are painted with a specific paint, black, blue, red, etc., etc. And it is important for us to know the quality of the painting, especially in a big machine, because a big machine containing several components may be painted over a different time scale. One part may be painted today, another part may be painted 3 months afterwards, and one might have been painted 2 years before. So, all those parts come together whenever there is an order for a big machine, all those parts are put together to make the car or whatever is the machine, and then at that time the painting quality of 2 years before and 1 month before and right now today, everything should match. Otherwise the car or a big machine will look like an assemblage of different colors, which is not aesthetically good, and the quality also suffers. Therefore, it is important for us to determine the quality of the paint or the surface reflectance. So, if the reflectance whenever light falls on the metal plate, it reflects part of it. So, the reflectance spectrum can be taken as a quality component for many of these things. So, we need to do this spectra of the solids, and in the real world we have turbid liquids, powders, opaque materials and translucent substances like polythene and other things, and then glossy paints and paints applied on metals, glasses and walls. So, all these things should need to have a uniform quality of the paint all over the surfaces. So, it is important for us to check the reflection properties of the paints and solids, other solids also. Quite often we do have to do that. So, let us have a look at what are the things involved in the spectra of solids. Quite often in the real world, as I told you, that turbid liquids, powders, opaque and translucent materials are encountered. They may be glossy or they may be semi glossy or they may be non-glossy also. So, the reflection of the incident radiation falling on such compounds can be measured for quality control. So, what do? We make a specular reflector available as a standard accessory to spectrophotometer, one more accessory for a spectrophotometer. So, this accessory should be able to tell us how the surface of a painted material or plated material. Electroplating also is done on number of materials, and the quality of the plating can also be determined by the reflectance spectra. So, what I want to show you is how we go about doing this. What we want to do is prepare our incoming radiation is like this H mu, and then I have a small sample compartment, okay, and I have the sample mounted here, okay. Then there will be the radiation will be falling on the sample surface and then it will be reflected. And if I fix a mirror here, then again it will reflect and then again it will go back and then again reflect, go back, like that. The constant, if I keep a hole somewhere here, the radiation H mu can be determined, which is a reflection, which is a quality on the reflection of the material which is pasted on the sample here. Normally what I do is I would if I have to standardize a given material, what I do is I take a standard reference material. This could be magnesium fluoride or calcium fluoride, TiO2, titanium dioxide or any of the standard materials. This is a white material. So, this white material I take it in a cup and then put it here and press it. So, this gives me a uniform face on which the radiation will be coming in and then it will be reflected. So, the angle of reflection I collect the radiation at the angle of reflection. So, it is as simple as that. What I can do is for a given sample, that is for a given painting, I can adjust the outcoming radiation, reflected radiation to about 80% or 90% or maybe 50% by adjusting the incoming radiation. This is radiation adjustment for the standard. How do I do this? This is done by opening the slit. If I open more, it will be adjusting to around 90%. If I open less, it will be adjusting to around 80%, something like that. And once this standard is set, all other materials can be tested according to the preset standards. So, this is the normal mechanism. An accessory to this effect will be available in spectrophotometers, but you will have to ask for it. Normally, whenever you meet somebody who is trying to sell you a spectrophotometer, he will not tell you that an accessory like this will be available. 99% of the time people do not want to tell you what are the accessories, because it will affect their sales business. So, if you buy a special equipment for every application, the seller will be happy, but a buyer will be happy if he does more applications with a single instrument. So, it is your duty to have to know about such things. So, coming back to the spectra of solids, quite often we come across situations like this, and then the sample compartment needs to be modified with respect to solids, because if we have to make the color measurements. Since every contact of light beam with a solid particle results in specular reflection at every few millionth of a centimeter, any surface appears uniformly bright in all directions. Okay. So, the quality of the painting or an electroplating or a thin film prepared in a laboratory, all these things can be standardized using a reflectance term that is known as sheen or gloss. Sheen is SHEEN and gloss is, of course, I think many of you are familiar with the word. This is the gloss is the diffuse component of any material that is colored, otherwise it appears white. Okay. So, that is the definition of gloss. So, the whiteness and reflectance of increase as the diameter of the component increases. This is a very simple conclusion. You do not have to be a mathematician to say such things, but the reflectance of a substance is also a semi empirical relationship. So, in this case what happens is we write a term known as S, that is the ratio of log of P naught by P, that is just like Beer-Lambert's law, but that is a function of a constant k into B C d cube divided by d raised to 4 plus alpha into lambda raised to 4. The relation is somewhat complicated, and here small d refers to the particle parameter. Here I have the small d, that is d cube, and lambda is the wavelength, c is the concentration, here I have it in the numerator, b is the path length, k is a geometric constant, and d is a method constant. So, for every, whether you use calcium fluoride or titanium fluoride, capital D will be different in the slide what I had shown you earlier. So, alpha is again a standard parameter that is related to lambda. So, known values of lambda alpha are available for each wavelength we choose. So, it may alpha is different for UV, different for visible, different for near IR, like that, and basically you can see that log of P naught by P, that is absorbance, is a function of all these things. Here path length is constant, the particle size is constant, you should try to keep it that way, most homogeneous way, and capital D, that is method constant, is automatically fixed, and lambda is fixed, and if lambda is fixed, alpha is fixed, and k is a proportionality constant, right. It is a geometric factor, but basically it is a proportionality constant. So, you can say that log of P naught by P is proportional to concentration. That is how the painted materials can be determined. So, for using a reflectance, as I had told you, a magnesium oxide standard is employed as a reference, and all other measurements are made with reference to this standard. And the applications definitely include paints, textiles, paper industries, thin film industry, and any other large surface area preparation with different colors. That is how we should be going about it. I want to take you to another level of spectrophotometry, practice of spectrophotometry. Now, that is fluorescence and phosphorescence spectrophotometry. Normally, we are concerned in 99% of the time about the changes in color as far as spectrophotometry is concerned. But whenever there is a radiation impinging on a substance, the substance, when it absorbs the radiation, naturally the radiation that is coming out will be less than the incident radiation, because part of it is absorbed. Now, there is another phenomenon known as fluorescence. What this fluorescence does is it will give out different colored radiation than the incident light. This phenomenon is known as fluorescence. Now, you have seen fluorescence in your day to day life number of times, number of places. Quite often you will see the fluorescence phenomenon in on the highways. Whenever your car is going, it falls on a reflecting plate, it will show you the road signs, etc., in different colors. So, if you go to airport or in your own city at night, when the traffic police or somebody who is a functionary, they will be wearing a different coat with green color, red color, etc., and whenever there is red light falling on the any light falling on the person's coat or something, it will show different color, and it makes him appear specifically focused for a particular job to be done. This sample what I had shown you earlier is also a phenomenon, and if you look at it from the bottom, you can see there is certain amount of blue color associated with this, otherwise from the top it looks reddish. So, different colors are possible to generate from the same incident radiation. So, this fluorescence phenomenon can be instantaneous, taking place very fast within a matter of about few seconds, and then you do not see from a practical standpoint of view, The moment you see the person wearing a fluorescent shirt or fluorescent pant, fluorescent shoes, fluorescent road sign, etc., even though there is a time gap of about 10 raised to minus 8 or something like that, 10 raised to minus 12 also seconds, then your eye will not see a time gap. So you will see instantaneously the different colors of fluorescence. And many of you may remember at homes the in the older times clocks used to give you visible numbers at night without any light. So they were also known as fluorescing clocks, but they contain radioactive materials which used to give out radiation. So that is also a kind of fluorescence only, and sometimes what happens is this fluorescence may take more time. It may take about 10 seconds, 5 seconds like that from several minutes. Once the radiation impinges, the radiation that comes out may come out after a small delay. So that is visible. That means you can experience the time delay also. Such a phenomenon is known as phosphorescence. Now fluorescence and phosphorescence both are a sort of extension of the spectrophotometry, and quite often the accessory for fluorescence is available with many manufacturers. So if you are in this business of measuring color, it would be good to have a fluorescence accessory, but over the years fluorescence has developed as a separate special new science, and dedicated fluorometers are also available, but essentially principle remains the same. So what I would like to do is in the next class, next two classes, I would like to teach you a little bit about the phenomenon of fluorescence, how it occurs, why it occurs, what are the instrumentation, etc., and what are the components, and then we will move on to the applications of spectrophotometry to different parameters in water monitoring. So thank you.